Hi, welcome to the next session of an Intro to Data Analysis. Today we'll be focusing in this session on visualization, grammar, and theory, and to help us to understand how do I make using theory-based decisions. In the next session we'll be focusing on visualization design, particularly the relationships between variables, and that'll help us to be able to answer the question, how do I make blank to show blank, and also what patterns am I looking for? And if you remember, we started our journey in visualization with ggplot2 when we began to understand R. From there we moved into data transformation with dplyr. We learned how to select, filter, arrange, mutate, and summarize. Also, we used group by as well. And now we're moving back into data visualization with ggplot2. We'll be applying some of what we learned in data transformation in visualization. This will allow us to create summaries and add summary layers to plots. We'll be using ggplot2 and dplyr to do this. And if you remember, this is the boilerplate for ggplot2. You can supply data, geomes, and mappings. In particular, today we'll be focusing on the supplying of geomes and the mappings, and this is where theory comes into play. Remember that you can also add additional layers to a ggplot object with additional geomes, and you can even supply a different data set to different geomes. These are the geometric shapes that are available to you, but for the most part the four geomes you need are points, lines, bars, and boxes, and these are typically the most effective geomes that you can use. Remember also that you can take data and you can map variables to geomes, and you can also map the variables to the aesthetics of those geomes, and then you can plot them. But you can also take an aesthetic and you can set it to a constant, like here we set the color to blue. Today, we're really focusing on giving relevant theory for selecting geomes and mapping aesthetics. So our brains are wired in a particular way, and if we can harness some of that wiring and understand it a little bit, it can help us to make better visualization choices. So we really want to serve up some of the most relevant ways in which our brains are wired. And to help us to understand that, hey, our brains indeed are wired in particular ways, I'd like you to take a look at this visual right here. Look at the side A, look at the side B. And you'll notice that A appears to be kind of bulging out, whereas the circles on B tend to look like they're caved in. Now I'm going to go ahead and do something. And that relationship should have flipped. Now A appears to be dented in and B appears to be bulging out. Well, why is this? And it's the way our brains are wired. We think that our brains are perceived that light typically comes from above. Maybe it's because of the sun. But in A, the lighter part of the gradient is at the bottom of the circle. So our brains tell us, hey, the light comes from above. These circles must be dented in. It's the only reason it could look like this. And for B, conversely, we say to ourselves, well, the tops of these are light and the bottoms are dark. These must be bulging out. So this is one example of how our brains are wired, and our brains are indeed wired in particular ways. And if we can harness this, we can make our plots more effective for communicating to ourselves and to others. It's also important to realize not all these design choices are equally good. So for instance, let's say we had four people and we wanted to show the relationships between those four people. Here are two designs to show those relationships. Both of these relationships are equal. Both plots are showing the exact same thing, but obviously design one is much better at showing that. So it's important to realize that some design choices are definitely better than others. And you really need to understand some of the theory to be able to make the optimal design choices for displaying information. And probably one of the most important theoretical aspects to understand to make graphics that communicate effectively are pre-attentive attributes. And the mantra is maximize pre-attentive attributes. I say it again, maximize pre-attentive attributes. So you might be asking yourself, well, what is a pre-attentive attribute? I think the best way is to show it to you. So I'm going to give you a task. Go ahead and look at these digits and find all the 2's and count them up. Are you done? It's kind of a hard task, isn't it? Let me make it a little easier. I'm going to use a pre-attentive attribute of color to make this task easier. And now the task is much easier. And the reason is I've added the pre-attentive attribute of color, and our brains perceive it pre-attentively. It's almost effortlessly. It's extremely fast. It's as if though we don't have to apply much, little if any attention at all to the task because of that pre-attentive processing. And there's lots of pre-attentive attributes. This comes from Stephen Few, and here are some of them. And some of them are good at showing quantitative information, and some are better at qualitative information. So what ones are good at quantitative information? Well, the blue ribbon goes to 2D position. Length takes second, and in size, if you need it, can be third. And these are the types of plots that harness these pre-attentive attributes. So scatter plots harness 2D position. The bar plot harnesses length. And then here we see a bubble plot. So indeed, this is a scatter plot. It does harness 2D position, but it adds a third quantitative variable, and we're using size to show that third quantitative variable. So what pre-attentive attributes are great for categorical data? Hue is really good for that, and then shape is as well. So here's an example of how we'd use this in a plot. And of course, if you don't need both of these, you could actually combine them and make the highlighting of the two groups even more effective. So I've been talking about mapping data to these pre-attentive attributes, right? Well, that sounds pretty familiar. It sounds a lot like ggplot, right? And indeed it is. ggplot2 is really great at using theory to be able to make effective plots, right? So in particular, the geomes, you can map pre-attentive attributes to the geomes. That would be things like 2D position, or it would be length when you're choosing bars or points. And then also the aesthetic mappings can enable you to make pre-attentive choices. But a bit of a caveat is I've been saying maximize pre-attentive attributes, right? But you look at this graph and you might scream. It's because you're getting an overload. When I say maximize pre-attentive attributes, I don't mean show a bunch of them. What I mean is use them to their fullest potential, right? So it's not like Jello. You can't just keep adding more. There's not always room for Jello, you know, or room for more pre-attentive attributes. In fact, if you get too many of them together, like here, your brain can no longer process them pre-attentively. So you want to really use them in ways that are smart to show the relationships that you're interested in, right? So the two big takeaways here are data maps to pre-attentive attributes. And ggplot2, you can harness these pre-attentive attributes when you select geomes and also when you do the aesthetics mapping. Let's code. So the first thing you should do is to load the dependencies here and then also view the data sets. Pause the video and do that now. So after you've loaded these two packages, the data sets, Buffalo Snow Tidy, is one data set. This is an actual data set showing the snowfalls per month across multiple years, across multiple decades. That's a pretty interesting data set. And the second one is a quasi-authentic data set in that it's fictional characters, but it is true attributes about them. And so that's a pretty interesting, fun data set to work with as well. Okay, let's move into selecting aesthetics. So the very first plot we're making here, it asks, what's the distribution of eye colors, right? So we want to compare counts, right? So bars, that'll use the pre-attentive attribute of length. So that's a easy choice here, right? So we start by taking our data set, passing it on to ggplot2. I want to pause for a moment here with you. And you're used to seeing the data set inside of ggplot like this, like data equals comma, right? That's how I've typically been showing it. But since data is the first attribute to ggplot2, we can use a pipeline. And so we can just say Star Wars, pass it on. And this becomes useful if you want to do something to the data in between. Let's say you wanted to put some summarize in here or filter or something like that. It becomes much more useful if you can pipe the data forward. The only difference is once you get into ggplot2 code, the pipe turns into a plus. So two different pipe symbols. Now, we pass Star Wars onto ggplot2. The first argument is data. Then the aesthetic is eye color. That is the X variable, right? And I could have been explicit like this. Typically, we aren't for the X and Y in ggplot2, but you can be if you want to. And then we pass or pipe that on, and geom bar is how we're going to represent this data. And you can see here that I am using a constant fill of orange, and it will fill the coloring with orange. If you do color equals instead of fill equals, it'll actually change the border coloring, not the fill of the bars. So let's go ahead and see what that looks like. And this is as we expect, right? So we have different groups, and the lengths easily allow us to compare. They're not ordered. That would make it even easier, and we'll learn about that in future. But for right now, we can see, yeah, brown is the tops here, and we can see blue is close behind. So the length allows us to easily compare these quantitative values. You might say to yourself, you know what, there's actually two different variables being represented here. There's eye color, but then there's counts as well. How come we don't supply counts? And the reason is geom bar is actually computing the Y for you on the fly. So I just grabbed geom plot. I'm going to stick it into the console and hit enter, and it'll show us the code. And we can see here stat equals count. So what it's doing in the background is the geom bar is computing Y for you, right? And we could do that ourselves. We've learned the skill set using dplyr to be able to make counts. And we're actually going to do that so you can see how you could do that yourself, right? So keep in mind that the geoms have built-in stats that are sensible, right? Sometimes you might want to override them, and geom bar is probably the one you will most commonly override. Let's take a look at another one that is kind of an interesting one. Geom bar. In the stat for geom bar, oops, I did not mean geom bar. Silly myself. Geom box plot. And we can see the stat is actually box plot. So that's kind of interesting. There's a specific computation to compute the 5 different values that are needed for a box plot. Okay, so let's go ahead and create a second plot here, a bar plot. But instead of allowing ggplot to compute the Y values, we'll do that ourselves. And we'll use, we'll have to do a group by here. And we're grouped by eye color, right? and we're summarizing, so we use a summarize, and we want n equals the length of eye color, right? So we could type that on forward, right? And keep in mind there are a couple shortcuts we could have done here. One is the n function, and that's a shortcut for length wrapped around a variable, and you get the exact same values. But there's an even nicer shortcut I talked about last time, where we can just, instead of group by, use count, and we don't need to summarize at all. So it's a shortcut for summarize and group by when you're doing a count. And we'll run that code, and you can see it's exactly as we'd expect, or exactly as the previous counts that we computed, right? So now we're going to pass that on forward to ggplot2, and we can say y equals n, right? So now we have the y-axis, what we want that to be. And if we ran this code, we are going to get a hideous, terrible error that will make us feel badly about ourselves. And the reason is because of that default stat in geombar, and you're competing. It's trying to compute y, but you're passing it y, and it's confused. So what you need to do is actually override that default stat. And instead of stat count, we want to do stat equals identity. And that just basically means use the y that I passed on to you, okay? And we'll go ahead and run that. And you'll see that we get the exact same plot that we did before, that ggplot computed the y value for us. And that can be useful, particularly if you're passing in a summary count to a plot, and you've already plotted the raw data somewhere as well. And this is probably, like I said, most geoms are have very sensible defaults. You don't typically need to override their stats, but geombar, I often do override this stat with stat identity. All right, next it asks us, hey, instead of filling this with a constant color value, fill it by gender instead. Okay, so here we actually use AES, fill equals gender, and the reason we wrap it with AES is because we're actually mapping it to data. So that's kind of interesting. A little hard to see though, right? Because the legend made the plot area a little more squished. So in the next section we have added coordinate flip to it, or chord flip, and you can see it flips the bars. We learned about that previously. So that's pretty interesting as well. All right, let's move along. It asks, what's the relationship between height and mass? And as soon as you hear two quantitative variables, really your default there should almost always be a scatter plot. And a scatter plot is really a geom point. And both of your x and y variables are quantitative, right? So that's what I've done here. We pass star whereas on, and AES, we say x is height, y is mass, and represent that with geom point. We do that, and we can see, yeah, there's a relationship, but there's a couple of things that kind of flag right away to me. And the first is in the console, we can see that 28 values were removed. They're missing values, either height or mass, or both were missing. So we probably want to investigate this further and understand why are these values missing, right? But the next thing that kind of pops out to me is there's one value here that is way outside of the normal range, and it's probably skewing the rest of the data below, or at least our perception of that data. So we might want to understand what is going on here. So we realize that most of the characters are well below 250 for the mass, and I think that's in kilograms. If we want to see more, we could use question mark and then Star Wars, and we could understand what that mass is. But we have the skill set to be able to filter out and figure out who that character is. So we just take Star Wars, filter, and I want to know where mass is greater than 250. Right away, Jabba the Hutt, if you didn't already guess it. So that makes sense. So I want to replot this data, and I want to remove Jabba from the data set. So how do I do that? Instead of saying, give me the characters greater than 250, we're going to filter him out by saying, give me the characters less than 250. We'll pass that on, and we'll relook at the relationship with the points. And here we see it's not quite as linear as I thought originally. Maybe there's a little more curve to it. Next, it asks, does the height-mass relationship hold across genders? So it's asking for the exact same plot, but we want to add to it categorical data. And one of the best ways to do that is with color. So here we have same exact plot, but instead of no color, we're going to say color equals gender. And because I'm mapping that to data, it's again inside of AES. And that allows some things to rise to the surface, but still kind of hard to see a little bit, right? Maybe we learned that color and shape are two different ways to pre-attentive attributes to show categorical information. So maybe if we used shape instead, so we map shape to gender here. Maybe if we did that instead. And that's actually probably worse. We see triangle, circle, square. But you can actually and I think it's worse because of the default choices here. So we can actually override these default choices of shape using scale shape manual. And that's not the point of this so much, but I am showing you, hey, this is possible, okay? We don't want to focus on it, but I do want you to realize this is a possibility, and you can play with that on your own. And what I'm doing is changing the three plotting values from circle, triangle, and square. I'm changing them to these values here. And I don't have these numbers memorized. You do have to pass it in numbers, but I Google it almost every time because I use it so infrequently. I just don't have time to waste, or the cognitive space to waste on memorizing it. So I Google it, like something like ggplot point shapes, and I get something that looks like this, and I pick the appropriate shapes, right? And the appropriate numbers for those shapes. So that's what I've done here. And I pass in the particular shapes that I want. So that helps make things a little bit clearer. But I also said, hey, we can actually be redundant with this, and we can pass in both shape and color for gender, and that's what I've done here. Shape and gender is mapped redundant, shape and color is mapped redundantly to gender. And we already learned about scale, shape, manual. I figured why not throw in their scale, color manual as well. And this is a little easier to deal with. You can say values equals, and it's a vector, and you can give it the colors you want. It also takes hex values as well. And that really makes things clear. In fact, we can see that there's none for gender up here. We can see that kind of popping out that we couldn't see before. We can see females towards the middle here that are red X's. Really makes things pop pretty nicely when you're using redundant shape and color. Next it asks, are older people heavier and taller? So it's asking for 3 quantitative variables: height, mass, and then age or birth year, I guess, in this particular instance. We don't have to necessarily compute age. I guess we can compute birth year, right? So we go ahead and we keep the plot as we have been, height and mass, but we map birth year to size. We're going to create a bubble plot here. Because remember, when you have 3 quantitative variables, this is a go-to where you use 2D position and then you add to it size for the pre-attentive attribute, right? And I can't say that we necessarily can answer our question, but something interesting does pop out. There's someone who is very short, very light, and very old. Who is this character? And you might have already guessed it, okay? We have, though, the filtering skills from dplyr to be able to figure out who that person is really quite quickly. There's a number of ways we could narrow this down. We could say less than probably 50 for height and less than, 30 for mass. But I'm choosing a mass of less than 250 and a birth year greater than 500 because this is a really large birth year. So I run that, and we figure out right away it's Yoda. And you might say to yourself, well, why didn't you just do birth year greater than, not birth year, why didn't you just, do birth year greater than 500? Why did you need the mass less than 250? And it's because of who we didn't plot. And when I commented out that line, you see Jabba the Hutt is also extremely old. Something else to point out here, I used 2 different filters, and I just piped it forward. I could have also have used a Boolean AND statement as well and got the same exact results. Next question asks, is this correlation between height and weight consistent across species? So this is just simply changing out what we're mapping color to and map it out to species instead of gender, right? And here we have everything, and it's just too much. So the first question we might want to ask ourselves is, are there species or groups we could combine? And so we have the skills to be able to do that. We take Star Wars, we filter out Jabba the Hutt, we do a count on species, and then arrange that descending by n, right? And we can see that, for the most part, the majority of these 31 observations are human, 22 out of 31, and maybe we want to see that probably against everyone else, because all the other groups are rather small, right? So we need to regroup or categorize that species variable into, we'll call it human and other, something along those lines. And we have the skill set to be able to do that too. We're going to use a mutate. We're going to call this new variable human. We're going to use case when. We say, when species equals human, it's human. Everyone else, it's other. And we can see what that looks like. We'll select species and human. Right? Sensible. And we're just going to pass that along to ggplot2, and where we had species for color mapping, we're now going to map it to human. So that adds to it a little bit. We can see humans don't fall too low on the height, and they don't fall too low on the mass, and they don't have the upper heights that the non-humans do as well. So it starts elucidating things a little bit. Faceting is another way that we could kind of tease some of this information out. It can be useful sometimes, but not always. We're going to head back to our slide for a moment. So there are 2 types of facets we can do in ggplot. One is a wrap, where usually we typically have one faceting variable or one grouping variable, you might call it, and you just want to make a subplot for each of those and just wrap it right around, just start filling in the rows until you run out of groups, right? Another one is facet grid, and you typically use this when you have 2 grouping variables, and you want to treat it like a lookup table or like a correlation table almost. And you have, for instance, here, looks like sex, female and male, and you can see where it intersects with the, I don't know what the DM, DO, and DS are, but it intersects with each one of those groups, right? So let's actually see faceting in action. So we're going to take that code we just ran, where we colored it by human. Instead, we're going to facet wrap. We're going to add to it a facet wrap here, and we're going to give it a formula. And formulas are used quite a bit in modeling in our, for instance, for like a regression or a linear type model, right? And it is usually 2-sided, where you have, typically it's a y and an x, but in this case, it's just the two grouping variables we want. And if you only have one grouping variable, you supply to it just on the right-hand side, and you don't supply anything on the left-hand side, right? And then we can also pass to it how many columns we want. So let's go ahead and see what this looks like. And you can see it broke out the human and the non-human into two separate facets, or two separate plots. This is sometimes called small multiples. And I'm going to get rid of that n call equals 1, and you can see what the default would have done. So you can choose to force it how many columns you want or how many rows. Okay? Let's keep working with this a little bit, and let's see what facet grid looks like. So it says, is there a correlation between height and weight consistent for humans versus non-humans? That's one facet variable. And then also males and females. And when you have two variables like that you want to facet on, typically you want facet grid, right? And you can see those two variables there, gender versus human. And then I've supplied to it scales equals free as well. And we'll talk about what that does in a moment. Let's go ahead and plot it first, though. And we can see, oh, we can actually look up human females, and there appears to be 3 of them. We can look up human males in the bottom left-hand corner. There's quite a few of them. We have a bunch of other males. We have a small cluster of other females. And it seems a bit strange that they're all clustered in one area, and I'm kind of wondering why. Also note that I used scales equals free. And you can see on the bottom x-axis that the human panels go from 150 to 200, whereas the others has a different scale. And that's because I said scales equals free x. We could also do scales equals free y as well. Let's see what that looks like. And you can see different scales for males and females. I could allow both scales to be free, right? Or I could force them to be fixed, and that's the default of ggplot2. And so that you're comparing everyone on an equal scale. So you have to ask yourself, do these scales need to be free in order to allow an equal comparison? And you have to be transparent about what you're doing. You shouldn't be using scales equals free to trick the reader into thinking that there's some sort of effect when there really is not. But it can be a useful tool. All right, we're now moving on to adding summary geomes. And we'll head back to our slides. So a plot is made up of multiple layers, particularly a really rich plot like this one here. You have raw data, you have a regression line, you have a regression formula at the bottom, you have scales, you have legends, you have labels, and just all sorts of things, right? But you can kind of break this out into 3 different components. You can break it out into your primary data components, right there. That's your points and your categories. You can break it out into secondary components. These support the primary data components. So you have things like the legend, you have the regression line, you have the regression equation and labels and such. And then you have non-data components that aren't related or to the data at all, don't come from the data, right? So you can actually, with ggplot2, change and alter all these different aspects and all these different components. But for this particular course, we're going to be focusing on the primary data components and theory and mapping to those, and then also the geomes in the secondary data components, particularly things like that regression line and the equation that would have been possibly created with something along the lines of geome text possibly, but in particular that regression line. Okay, so let's move back into our code, and we're going to be examining those primary and secondary layers, right? So let's go back to our original plot with mass and height, right? And now it's saying multiple aesthetics set to constant values. So this is just kind of useful to see that we can adjust all sorts of things set to constants, things like alpha, things like shape, fill, color, size. Let's go ahead and plot that. And that's actually quite useful for overplotting, right? You can do things like secondary components here. I'm going to take our original plot, right? We're getting pretty used to now. And we're going to add another layer to it with geom smooth. And we're going to add a regression line, and we're going to use method equals linear model. And we're going to not use the confidence intervals. To do that, I say fill equals NA. Let's see that. So we plotted on it a line, and you can see now a little more clearly, hey, this data is not quite linear, right? Up here to the top, we see quite a number of points that are far away from the regression line. So we might want to fit something of a curve to this, okay? And I'm going to get rid of that fill equals NA for a second. And you can see here the confidence intervals are plotted. They can be useful sometimes, sometimes they get in the way, depending on what you're trying to show. Okay? Next it asks, adding a regression trend line and faceting by human versus non-human and male versus female with margin totals, right? So this is a pretty complex plot. We're going to start with simple. right? Pretty simple right there. And note that I did also filter out so that we only have males and females. That's it. No other categories of gender. And we've plotted human to the color, right? Now the next thing I'm going to add to this plot is a secondary data component with geom smooth. And this will compute the summary statistic for me. I don't have to compute any summaries. geom smooth does that. It takes the raw data and computes the regression line for me. And so we can add that right onto the plot, as you've seen before. And you can actually see, wow, each one of those groups, human and other, gets their own regression line. So we're already getting complex. That's pretty interesting, right? Now we're going to facet it out by gender and human, and we're going to allow the scales to be free. And we're going to do something called margins equals true. That allows us to see really a lot of rich stuff. I'm going to give us a little bit more real estate here with the plot itself. And let's give it a moment here to re-render. Okay, the far right and the bottom are the margins, right? So that's, if you look at the far right here, that's for all females. The far right middle, that's for all males. The bottom regression line and points is for all humans. The bottom here is for all others. And the bottom right, that's for the combination of all humans and all others together, right? And then we've broken out human females in the top left. I think I said human twice. So human females in the top left. Then we have female others in the top middle. Then we have male others in the middle. And we have male humans in the left middle, right? So everyone gets their own facet. Really can start seeing some pretty cool trends here, particularly with females. They're quite a bit different than males. And maybe you see things by human versus non-human. So this is a pretty nice concept or tool that you can add to your tool belt with the facet grid, adding secondary data components like regression lines. I allowed the scales to be free. Maybe that's not fair. Maybe we want to see the scales not being free when they're held constant. Okay? So you have really a pretty nice tool set to work with. See that the trade-off is there now the human data plot area is very, very small. So you got to ask yourself, is the trade-off worth it? In this next section, we're going to do some more with selecting, aesthetics, faceting, and summary geoms, right? And we're going to be working with the Buffalo Tidy Snow dataset. So the first thing we're going to be doing is, it says, what is the distribution of snow totals across months, right? So we have month, which is, I would consider it categorical. You may have arguments otherwise, but I think that it best fits into a categorical type variable. And then we have snowfall, that's a numeric quantitative variable, right? So I'm going to do something that's interesting. We're going to use geom jitter. Up till now, we've used geom jitter for 2 quantitative variables, right? But I'm going to use it, and I'm going to allow the width to vary, and I'm going to say height equals 0. And we're going to see what happens when we do that. We get a pretty interesting plot that shows us the values for across those months, and this is for multiple years. So we can see quite a bit of variability in January. We can see quite a bit of variability in December. These also tend to have higher snowfalls as well. So that's kind of interesting. But it's kind of hard to see for some of these that have a lot of spread on them. Like, for instance, does January have, on average, more snow, or does December? So it's kind of hard to see that with this kind of spread. So we might want to add a little bit of information. Maybe we want to compute a mean for each of these months so that we can compare them. So we could do that as a table, but then we could add that information back into the plot as, say, another point, right? A colored point, for instance. And that just gives us another rich layer. So we have the tool set to be able to compute a mean for each of the months, right? So we take Buffalo Snow Tidy, that's our data set. We group by month, and we do a summarize on it. And here I also have added the min, the max, but the mean is what we're really after here. So let's go ahead and create that data set, and we call it sumdat. Let's view it. That's a pretty interesting data set. We can see the mins and the maxes and get a little bit of an understanding of the variability. So we can see like June, July. We're getting a pretty good understanding that these months don't have any snow, and that makes sense. We can see some strange Mays that have up to 8 inches. I'm hoping that's not for this May. So we can take this information now, and we can compute it, or we can then plot it now that we've computed it, right? So this is the same exact plot we had up above. Oh, not quite. We did not. We need to grab this height equals 0, right? Bring it down. And we can see that, indeed, hey, this is the same plot we just plotted, right? But we're going to add to it another layer. We're going to give it, this is geom point, we're going to give it the sumdat as the data set. We're going to set the aesthetic y equals the average from our data set up here, or ABE. And the reason I have to set it anyhow, and the reason I set that is because up above here in ggplot, I globally set the y value to snow and actually want to override it down here with y equals AVE. And then we have a constant value of blue set to those. Let's go ahead and plot that. And they're kind of small. Maybe we want to make them a little bit bigger. Size equals 3 maybe. We could start to see a little bit more. Maybe that's not standing out enough for you. Maybe red. Maybe different shapes you could play with. Right? I'm going to show you something else you can do. And I'm not going to do a lot of explanation on this, but I think it's interesting to see. I personally would probably use a segment here. And segments take y end, x, and x end. And we have all that computed in SumDat, right? I'm going to show you what that looks like, and you can tear that code apart a little bit yourself and figure it out if you would want to do something similar. So that segment allows you to nicely compare the values across months pretty nicely. Now I'm going to show another type of summary geom that we might use. That's geom crossbar, and this is great for showing variability. Okay, and it takes a y min, and a y max, right? So there's going to be 3 different points, and we're going to pass to it the average for the center bar. For the minimum, we're going to pass minimum. Or I'm sorry, for y min, we'll pass the minimum, and for y max, we'll pass the maximum value. So this helps us to see variability a little bit. I think it's easiest just to plot it and see. So this is the exact same plot we've been doing, but we're going to use the geom crossbar instead. So this gives you a little bit more understanding. You can see the raw data points underneath. You can see the bars above. You can see the center crossbars to understand what the mean is. You could actually use this with any summary. We could have used median with this. We could have used standard deviation. They all would have mapped to crossbar. But if we were after median and quartiles, something along those lines, we probably want something like a box plot instead. So I'm going to take the exact same plot that we just had, and I'm going to actually put the box plot first. I'm going to plot it underneath of the points, right? And we don't have to compute. I didn't pass in any summary data to it. I just passed in the raw data globally. Right here, I passed this in globally. So it is computing the 5 numbers it needs on the fly. And we can see similar type information. It's a bit more rich than the previous 2 plots I just showed. So we can see the median value. You can see the 75th and 25th percentiles. We can see outliers in blue dots and such. Next, it asks, can we add a lower to all the previous plot with the ranges? We can also add the ranges as well. I had to pause the video for a moment. It said we can add a lower, and that didn't make sense. We can add a layer. So I plotted this next code out that helped me to understand where the mistake was, and it was just a typo. So we're going to take some of the previous plots. So we now are going to add one more layer to it. We're going to use geom crossbar to add to it the min and the max, and we're going to say color equals NA, fill equals light blue. And in doing so, we can now create a box or a rectangle underneath that gives us the extreme values as well. So that can be useful. It might also just be too much as well here. And you'll note that I got rid of the actual coloring and by supplying NA to it. So let's see what it would look like if I didn't do that. And then it becomes too much. And if I would have gotten rid of that altogether, the fill, you can see how setting color to NA and fill to light blue, I can actually use the information to create rectangles with just mins and maxes. Okay. Could also accomplish similar type things with geom rectangle as well, or geom rect, I guess it is. Next, it asks, is the distribution of snow the same across decades? It says add color aesthetic and map to decade. Does this reveal anything interesting or overwhelm? So let's go ahead and do that. They want to know, first of all, we have a categorical variable month and then snow, right? And then we're going to use similar type jitter plot that we used above, but this time we're going to map color to decade, right? So let's see if this overwhelms or not. And I would say it overwhelms. It's really pretty difficult to know what's going on. So this is where that faceting really could be quite useful. So we're going to facet on decade and see if that kind of reveals anything. And now it does. We can see a same general trend across decades, right? We can see that the 1940s seem to be less variable. Also 1960s less variable, and maybe there's a bit more variable in the 2000s and 2010s, maybe even the 1990s as well, particularly with the June and July. And if we need to, not June and July, I apologize, with January and February, let's give ourselves a little more real estate. Maybe we can see a little bit more here. we can see that maybe back in the 40s and 60s there was more snowfall possibly in the November era, October, November, and as of recent, maybe not as much. These are kind of just all me kind of eyeballing it though. It's quite a bit of information. These are just kind of guesses, kindas, maybes. We don't really have anything conclusive though. Next it asks, summarize the snowfall across months within decades and replot. So here this is grouping across decades and months, and we want similarly min, max, and mean. So we're going to be quite a bit more rows than we had before. So we have 96 rows here, one for each month within each decade, right? And it asks us to replot. And we use this summary data as our new data set, right? And we have month in the average, and we plot it as a geom line. And a geom line is a really nice way to show changes over a timeline, right? And we could see that generally overall the trends really appear pretty close to each other. There doesn't seem to be a tremendous amount of variability. Maybe a couple points here. We don't necessarily know what decades these are, but we see some extreme values possibly here, possibly. Okay. Next, it asks, add a summary trend line. Notice that there are two summary data sets being used. Okay. So we have the data set we just created, and then SumDat as well. And we can see that SumDat is used for geom line, and it's also used in geom point. That means that this geom line right here is using the decade month information, right? So that's what we just plotted. Add a summary to that. This is where we pool all the information together. And let's add some points to it too. You can see that it adds a bit of training to the eye and allows us to see the central tendency for each of those months. So that brings us to the end of this session. Let's recap what we learned theory-wise. We learned that quantitative data can be represented with 2D position, with length, and then if need be, with size. We learned that categorical data can be represented with hue and shape, and they can be mixed together. We learned that there are different components of the visualization. There's primary data components, and then you can add layers to produce secondary data components, particularly to summarize the data with ggplot2. And then you can use dplyr to create those summary data sets that you pass on to those new layers. So let's go forth and apply this.